G'day, guys. How's it all going? So, just apology for the voice if I sound a little bit funny. I am recording this early in the morning. The reason for that is I tried to record this video last night, but it was just too hot. So now it's a little bit cooler. Now it's early in the morning, so I decided to get up because I pretty much just slept a full sleep, even though it's only 4:30. Uh, and so I thought I'd get up and actually record a video. So I digress. In this video, we're going to talk about integers. So I think if you're a programmer, you know what an integer is. And even if you're not a programmer, you might know what one is. But for those who don't, an integer is essentially just a whole number, right? So it's a number without decimal places. So just think of like 1, 2, 3, -5, those kinds of things, right? So they have a purpose in programming, and they're usually used quite frequently, right? So in Rust, we have many integer data types, and it's all based on size. And what I mean by size is essentially the number of numbers, I guess you could say, that fit into that type. So, for example, if I do something like this, I go let a number, whoops, equal, say, 2. We all know this is an integer from previous videos, right? And in fact, we know it to be what we call an I32. But I never really explained thoroughly what that meant. And essentially what that means is this number or this variable here is stored as an integer that is 32 bits in size. And not only is it 32 bits in size, but it allows negative numbers, or what we call a signed integer, right? Which means that we can allow for negative numbers in this data type. Now, the range, it's a little hard to calculate, but basically, overall, it's usually the total numbers that you can have is 2 to the power of 32. That's why the 32 is there. But the range is somewhere in the large negatives. I think I can't remember off the top of my head what it is, but essentially it's negative 2 to the power of 31. No, negative, 2 to the power of 31 to 2 to the power of 31 minus 1. It's something like that. I can't remember exactly off the top of my head. But essentially, you don't really need to know that. That's more the math side of it. But overall, it has a range, all right? And I'll show you in a minute what those ranges are in terms of I'll be bringing in a snippet of code just to give you an idea. But just understand that inside of the variable, we can use up to 32 bits of information to store a number, okay? A better example or an easier way to visualize this actually is to store this as, say, an I8. So this is a number that is stored in 8 bits of information, which means, and I know this out of the box, you can store between the ranges of 127 negative, all right, negative 127, negative 128, sorry, to 127. All right, so that is the ranges that you can store inside of an I8 because, right, 2 to the power of 8, right? So this is the math side of it. 2 to the power of 8 equals 256, right? So you might be wondering, why is the max number not 256, right? Well, first we have to account for 0. 0 is actually a number, which would reduce this down to, if we have 256 options and 0 is one of them, then that means the highest number you think it could store is 255, right? However, because we have negative numbers, we take half of the numbers of 255 and we shift them to the negative, right? Which means if we try to halve 255, well, it's not clean cut, right? So 0 becomes a positive value in programming. So that means 0 to 255 are considered positive, and then -1, obviously the negative 128 are negative. So that means 128 of the 256 are going to be negative, and 127 plus the 0 is also 128 in the positive. And that's why we get this range, right, of numbers. And as you go up, we have other ones, like in the case of I16, now this number goes up again. I think it's negative 32,000. I think it's 638. I can't remember the exact number, but it's something in that range, right? But you'll see it's distributed the same. Anyway, this is not the best way to describe it. You'll see in a minute. I'll bring a snippet of code in, and that will give you a better example. But the thing to understand is that what happens if we decide to go outside the bounds of that negative 128 to 127 range, right, inside of Rust. Well, let's do that. Let's just set this to, say, 128, right? So that's outside of 127. If I save this, what's going to happen is Rust is already indicating that it doesn't fit inside of this data type, this 8 bits of integer information, right? So if I run it, it's going to throw a compile error. So the compiler of Rust has picked up that this is not valid, right? Not the runtime. That's the important thing here. The compiler, the Rust compiler said, you're trying to fit something inside of something that doesn't fit that size, if that makes sense. Maybe I'll just repeat that. You're trying to put 128 into an i8 when 128 can't fit in an i8. And it literally says it out there, literal out of range for i8, So it tells you what the Rust compiler error actually is, which is really good, right? And the same goes in the opposite direction. If I decide to put this as negative 128, then it'll be okay with it. But if I set it to 129, then once again, the compiler, or there's going to be a warning from my IDE, but then if I run it, it'll give me the same issue. It says I29 does not fit in the type i8, right? So it's good that Rust helps us with that. Cool? So I guess the next thing is just to have an overall understanding of all the types that we have. So like I said, these are what are called signed types. So we have an i8, we have an i16, right? We have an i32, which is the default that we see when we declare without that. So we know in the past, there it is there, right? We also have an i64, which is a 64-bit signed integer. We have a signed 128. Why is it not? There we go. 128 signed number. And we have this one called an isize, right? Now, this isize is essentially different, or could potentially be different, depending on the machine, right? So it kind of says there, on a 32-bit target, this is 4 bytes, and on a 64-bit target, it's 8 bytes, all right? I'm not too sure from what I've seen so far why you would use this. I would just probably go with the approach of, if you need a 64-bit number, you'll use a 64-bit number. If you need a 32-bit number, you'll store a 32-bit number, right? That's it. I don't think there's a major performance benefit of using an isize, but I'm sure Rust has edge cases where it actually means something. But to date, I haven't seen a benefit for it. But that's there, just for completeness. You also have what's called the unsigned integer. So you have what's called a U8, like so. And the difference between a U8 and an I8, right? And you can kind of see it with the error there, right? So this will be allowed. Actually, it won't be allowed. Let's just set that at 128. So it's allowed for an I8, negative 128, but for a U8, that's not allowed, right? So what is the difference between the two types? Well, essentially, a U, in this case, is called an unsigned integer. And an unsigned integer doesn't allow for negative numbers. So the minimum number we can store here is 0. Now, the beauty of using an unsigned integer is not only does it restrict the range, so in some situations you don't want negative numbers in your variables, but on top of that, it increases the numbers that you have that are positive. So remember, as I said before, an 8-bit integer can store 256 numbers or different numbers, right? But because it was signed, it was distributed across negative and positive. So you had negative 128 to 127. Well, for an unsigned integer, all those negative numbers are reassigned back to positive numbers. So now the range for a 8-bit unsigned integer, right? So unsigned integer is now between 0 to 255, right? And the reason why it's not 256, like I said before, is because 0 counts as a positive number, right? And we can test this. So if I put in 255 here and save, you'll see we get no compiler error. It'll complain when I run it because I'm not using the number or using the variable. But outside of that, it's happy. But if I try to set this to 256, right, which is outside the range, then once again, the compiler's going to tell us, right, which is really good. Now, this is the same as the I framework or the I types. You've got a U16, you've got a U32, you've got a U64, you've got a U28, and then you got that usize again, right? Like so. Right, so you've got all those types as well. And to better demonstrate what sizes they store and the minimum and max numbers, I do have a little snippet here, which I don't want to exactly illustrate at this stage because it uses things called functions, which we haven't discussed yet. But essentially, I'm going to copy the snippet inside of this file and then just paste it inside of main, and I'll show you what it does when I run it. So just to quickly explain what it does at a fundamental level, though, is for each type that I just spoke about, it gets the size of that type in bytes, it gets the minimum number and the maximum number, and it displays it as a print. It does this for the I numbers or the I integers and the unsigned integers, right? The U's. Cool? So when I run this program now, so if I go back to the top and I just click run, now you're going to get a set of messages down here. So you can see for, hang on, what's happened here? Where's my ints? Ah, they're up there. Okay, cool. I'm just going to make this screen a little bit smaller just to have it fit in the terminal a little better. And I'll just raise the terminal up so you can see it. But essentially, you can see for an i8, it's the range I spoke about just a moment ago, right? Negative 128 to 127. You can see that it uses up 1 byte. So a byte, if you don't know, is 8 bits in size. So 1 times 8 is 8 bits. That's why that i8 goes to that range. Then we've got the i16. That's 2 lots of 8 bits, so equals 2 bytes. And negative 32. That was the number I was trying to get before, right? That I didn't quite get right. Then i32 is 4 bytes. i64 is 8 bytes. You can see their ranges. 128 is even larger. And then we get down to the isize, where I said it's based on the architecture. This machine is 64-bit. So because of that, you'll see that the size is 8 bits, like the 64 or the i64. And you'll see the ranges are the same as the i64. Cool. Then we've got the unsigned values. So U8, like I said, 0 to 55. The U16, 0 to 65,535. And so on and so forth, right? And once again, U64 matches the same size as the usize because we're on a 64-bit machine. Cool. So that's on it. I want to quickly demonstrate that I'm correct about this usize and the isize variables. So I'm going to quickly jump over to my 32-bit machine and show you what the values are on that. So just give me a moment. Okay, so now I'm on a virtual machine of Ubuntu. In fact, it's Ubuntu 16 because it was the only one I could find that was 32 bits. And basically, I've rewritten a similar program to the one that we just saw, but now I'm just including the 32, 64, and size variables for both signed and unsigned. So you can see above, we've got similar code to what we had before, and then you'll see the same thing for the unsigned down here, right? Otherwise, it's pretty much the same code we saw a minute ago. But the results are different, right? So if we come down and look at the terminal down here, we can see that the i32 and the isize have the same number of bytes in size, right? And they have the same range. Same deal with a u32 and a usize. They're also the same. As opposed to before, when we were using our 64-bit machine, the isize was the same as the i64, and the usize was the same as the u64. So that just kind of demonstrates in real time what that actually means. But yeah, I just thought I'd point that out and make it a little bit more obvious to you guys as a viewer. Now, before I end the video, I just want to quickly talk about when to use these data types, because people might be wondering, well, why do I have to use, say, an i32 or an i8, or why is the default i32 and all that kind of stuff, right? Well, essentially, what Rust does is it says, okay, most of the time you're going to just store a number temporarily, and there really is no benefit computationally between storing it as an i32 or storing it, say, as an i8 or an i16 or whatever, right? And there's a little bit more processing power if you go with an i64 or an i128 or something like that. But generally, you're not going to need those numbers, and most people are going to use something about the size of an i32, right? So that's why it's the default out of the box. Now, an edge case where you might want to be conscious of, or there's a couple of edge cases where you might want to be conscious of the others, is when you're concerning yourself with storing a lot of numbers in memory. So say, for example, you only need to store, between 0 and 100 in a whole list of variables in your application, right? Say you're storing percentages or something like that, and you're going to have like thousands upon thousands of these variables stored in memory, okay? In that situation, you probably want to go with an unsigned 8 because that can go from 0 to 255, and it only requires 1 byte in size, right? As opposed to an i32, which is actually 4 bytes in size. So it's actually four times the amount of memory that the unsigned 8 would store, right? So that's just an important distinction. If you ever have a situation where you need to store a lot of variables in memory, just be conscious of the number of bytes that are used, right? So that's the first one. The second one is if you want to restrict a range of numbers to a certain spectrum. So say, for example, you want to store a 256 color palette, right? You're probably still, again, going to want to use a U8 because that can go from 0 to 255, right? Giving you a maximum of 256 potential combinations. So in that situation, you don't want to store it in, say, an i16 because then potentially you could be leaking extra values rather than the 256 colors you're trying to store. Yeah, something like that, right? So outside of that, though, I would just recommend most of the time you don't even declare what the type is. You just let it infer it as an i32 and move on, right? But for completeness, I just wanted to show all the different integer data types that were available and how they are stored and basically the min and max values that can be stored inside of each type, right? So that's where I'm going to end the video. So in the next video, we'll probably focus on floating point numbers. But until then, I'll see you all later.